morning, Manandal. Myself, Sreevani, working as an assistant professor in the Department of ECE in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn one of the topic in electromagnetic waves and transmission lines as applications of Ampere's law. So, this topic comes under static magnetic fields or magnetostatic fields. So, some of the applications related to this Ampere's law already we have discussed related to line current, surface current, as well as the third application or the last application related to this Ampere's law is here infinitely long coaxial transmission line. So, in order to learn about the application of this Ampere's law, we need to know first what do you mean by Ampere's law, how mathematically we can represent this Ampere's law. So, the line integral of L means circulation of L around a closed path, that is H dot dl is equal to the net current enclosed by that path. So, according to Ampere's law, circulation of L H dot dl is equal to I enclosed. Now, in order to determine the infinitely long coaxial transmission line case, the H field is to be evaluated. Now, to evaluate that magnetic field intensity as H, we need to remind first what actually this Ampere's law. So, that is integral L H dot dl is equal to I enclosed. Now, if we are going to apply the closed line integral of H dot dl around any closed path, means there we can consider different Amperian paths. Why? Because we are using here Ampere's law. So here is the one of the application of Ampere's law which we are going to learn now. So that is infinitely long coaxial transmission line. In order to analyze this one, we have considered an infinite long coaxial transmission line consisting of two concentric cylinders having their axes along the z-axis. Why? Because in the figure we have considered one z-axis that is out of this Amperian parts. And the cross section of the line is as we have considered. So, if we consider, here is an example for a coaxial transmission line. So, this is the outer core, inner core, and we have then there exists and cladding. Then, if you observe the cross section of this one coaxial transmission line, means if you cut this wire into half, then internal structure looks like the figure which we have considered for the analysis of infinitely long coaxial transmission line. So, there if you consider the 4 Amperian paths, those are representing with the path 1 is denoted with L1 and path 2 is L2 and path 3 is for L3 and 4th Amperian path we have considered here as L4. And after this path L2, we have considered the total current around that path is I, and after that 4th path Amperian path, we have considered the total current as minus I. Now, in each and every Amperian path, we are going to estimate how much is the magnetic field exist in that particular. Now, how much is the current total enclosed by that particular path. Now, by equating those two, we are going to get the equation for magnetic field intensity. So, consider an infinitely long coaxial transmission line which is consisting of two concentric cylinders, and if you observe here, the figure is the example for the cross-sectional view of the coaxial transmission line. Now, the inner conductor has a radius where A and carries the current I, and while the outer conductor which is having the inner radius of B and outer thickness as T and carries return current as minus I. See here, if you observe in the figure, so inner circle which is having the radius as A and outer circle has the radius as B and the thickness is given by here T along with the two currents we have considered I and minus I. So, depending upon those inner circle radius as A, outer circle radius as B and along with that thickness T, then we are going to estimate, we are going to calculate 4 Amperian paths around that coaxial transmission line. So, to determine H everywhere, assuming that current is uniformly distributed in both the conductors. Why? Because not to apply this Ampere circuit law, there must be a symmetrical current distribution is exist. So once it has been verified that symmetrical current distribution is exist, then we are going to apply the law called Ampere's law. So to determine H everywhere by assuming that current is uniformly distributed in both the conductors. Why? Because we have considered here a coaxial transmission means there exist two conductors, inner conductor with the radius as B and the outer conductor with the radius as B. Inner one as A and outer one has the radius as B. Since the current distribution is symmetrical, we are going to apply the law called Ampere's law. So Ampere's law along the Amperian path for each of the four possible regions. So there, if you consider the figure, in that if you observe, there exist 4 Amperian paths and 4 Amperian paths are given by here. First path, if you consider path L1, through that L1, the range will be the radius of that row is ranging from 0 to A. Hence, the field which is exist in that path L1 is considered to be as 0 less than or equal to rho less than or equal to A. And the next is second path is A. Path L2 is exist in the range that is A less than or equal to rho less than or equal to B. And for path L3, the range will be B less than or equal to rho less than or equal to B plus T. And for path L4, we used to consider the region as rho is greater than or equal to B plus T. So along with all the 4 paths, we will be considering the 4 regions are to be as 0 to A as for path L1 and A to B for path L2 and B to B plus T is for path L3 and rho is greater than or equal to B plus T case for we are going to consider the fourth path is said to be L4. Individually, we are going to estimate magnetic field intensity exists in the respective paths as L1 to L4. Okay, so for the first one means for the region where we have considered the range is 0 less than or equal to rho less than or equal to A, then we apply Ampere's law to path L1 is given by I enclosed is equal to closed circle integral L1 H dot dl. In general, it is given by integral L H dot dl which is equal to I enclosed. Now, this is the law which we are going to apply for the first Amperian path called L1. For that path L1, the range will be given by here 0 to A. Hence, in place of L, we just considered here as L1. So, I enclosed equal to closed line integral L1 H dot dl which is equal to I. And we know that the relation between the current and its density is given by integral S J dot ds. I equal to integral S J dot ds. Now, if we equate these two, H dot dl equal to I enclosed, then from this I enclosed, it is equal to integral S J dot ds. Now, from 3 relations, we can consider here I enclosed equal to closed line integral L1 H dot dl is equal to integral S J dot ds. Why we have considered here L1 means we are going to estimate the H value for the path L. Then since the current is uniformly distributed over the cross section of that coaxial transmission line, then we will be calculating the J value. So where J is said to be current density, then from this we are going to estimate how we are going to calculate this one. J means which is equal to, so I equal to, then J is to be considered as a constant, then integral S ds. Now here we have considered coaxial transmission line means then the coordinate system we need to consider is your second coordinate system as cylindrical coordinate system. So if we consider cylindrical coordinate system, those variables are given by rho, phi, z. And the differential variables are d rho, rho d phi and dz are the 3 differential components for cylindrical coordinate system. Now, in order to calculate this differential surface area, then we have to consider the direction of the particular surface. There, in the coaxial transmission line, we observe that is located along the z, means the direction which we have considered here as z direction. So, if you consider the direction is to be z direction, means and the rest of the 2 variables need to multiply, to get the value of this differential surface area. Hence ds is equal to rho d rho d phi into az is the formula for ds. Now from this I is equal to j into, so here if you observe from the formula rho d phi means rho and phi are the two differential variables. Hence surface integral S is replaced by rho is equal to 0 to a and phi equal to 0 to 2 pi rho d phi az dot az. So here az dot az value is 1, then j, then rho is to be considered as here rho square by 2. Then if you integrate here with respect to rho, then rho square by 2 is the result. Then if you substitute 0 to a and phi value, but you take it as 5, and if you substitute limits as 0 to pi, then it becomes j rho square by 2 means a square by 2 into 2 pi. So this 2 gets cancelled. J pi a square is nothing but I. Now from this we will be calculating the current density J, and that is given by I by pi a square with the direction as Z. Why? Because initially we have been considered here the direction for that is Z. So J can be obtained as J is equal to I by pi a square into AZ, where ds is equal to d rho d phi az, and that we have considered like this. Now from this I enclosed is equal to integral s j dot ds. Now I enclosed equal to integral s j dot ds, which is equal to, now substitute in place of this j by this formula means I by pi a square into rho d phi. So I by pi a square, again if you integrate this one, then it becomes rho square, and here if you substitute in place of phi, if you take it as rho square by 2 here, then if you substitute limits for phi it as 0 to 2 pi, then this 2 gets cancelled. Again the equation becomes pi rho square, which is equal to I rho square by a square. Why? Because here this pi and this pi gets cancelled. I into rho square by a square. So previously means here for the region we are going to estimate the magnetic field intensity is given by here 0 to a. Now suppose if you substitute in place of rho by again if a, so then a square and this a square gets cancelled, and I enclosed is equal to I for path L1, but it is not equal to for the path L1 the total current enclosed by that path, first path is not equal to I. Hence we just consider instead of the range for rho is 0 to a, we have considered here it as 0 to rho. Hence I enclosed is equal to I rho square by a square is we have got. Now from that equation means I enclosed is equal to closed line integral L1 h dot dl equal to integral s j dot ds. Now by comparing those two terms in the equation number 1, then we are going to get here integral h phi then dot dl is equal to h phi 2 pi rho. Why? Because dl is evaluated with respect to the z direction. So h phi then into 2 pi rho is equal to, and I enclosed value is given by I rho square by a square. Hence I rho square by a square equal to h phi into 2 pi rho. So rho and this rho gets cancelled. From that h phi equal to, we are going to get I rho by 2 pi a square. Okay. Now in the first path, if you consider the first Amperian path as L1, the range will be, and the region we have considered as 0 to a, then h phi component is to be obtained as I rho by 2 pi a square. Okay. Then coming to the next region we are going to consider is here the region is to be a is less than or equal to rho is less than or equal to b, then we use the path L2 as Amperian path. Hence the formula becomes here I enclosed is equal to closed line integral L2 h dot dl is equal to I. Now from the figure the total current which is enclosed by the path L2 is given by I. Hence I enclosed is equal to I for the path L2, right? Hence, and already we have evaluated, this is the formula for the rest of all conditions, it is similar. Hence, integral L2 h dot dl can be given by here h5 2 pi rho, which is equal to I. Now, why? Because according to this Ampere's law, that is integral L h dot dl is equal to I enclosed. Now separately we have evaluated the equation for I enclosed and integral L h dot dl. Finally, to equate these two, then you're going to get the equation for h. Then h5 equal to I by 2 pi rho. From these two relations, h5 equal to I by 2 pi rho. Okay. So from the second case means if you consider the region as A to B, then we use the path called Ampere path as L2, then that is the case H5 component is to be obtained as I by 2 pi rho as like this. Previously we have got for the path L1 that is H5 equal to I rho by 2 pi A square. Now coming to the second one, it is H5 equal to I by 2 pi rho. Now since the total current I is enclosed by path L2, hence I enclosed equal to I in this case. Next, coming to the third path means the region which we are going to consider is B is less than or equal to rho is less than or equal to B plus T. So we use L3 as the Ampere path, hence I enclosed is equal to integral L3 h dot dl, which is equal to h5 into 2 pi rho. So this already we are going to evaluate. How we have evaluated this one means already we have learned, that is integral L h dot dl. So if you are going to evaluate means that cross-sectional view of the coaxial transmission line. So this is the case phi direction we are going to consider. Hence integral h5 a5 dot dl means the formula for dl is given by for the direction of phi rho d phi a5, right? So rho d phi a5 if we consider for L means a5 dot a5 value is 1, h5 can be treated to be a constant, then integral L rho is also a constant, then d phi. So h5 into rho, then for path L the differential component is here phi means, so L means phi equal to 0 to 2 pi, then d phi. So h5 into rho, and if you consider that as phi, then limits if you substitute 0 to 2 pi, then 2 pi h5 into rho is the result for the equation, that is integral L h dot dl. Right? So this is the condition which is similar for all the 4 Ampere path and the regions of 4. So for the region here, B is less than or equal to rho is less than or equal to B plus T case, then we are going to consider path L3 as the Ampere path. Now I enclosed is equal to closed line integral L3 h dot dl equal to h5 into 2 pi rho. This we just evaluated this one from. Now where I enclosed is equal to I plus integral S j dot ds. Why? Because till path L2, the total current enclosed by that total path L2, it will be given by I. Now coming to the path L3 means along with this I, we are going to consider its density as I plus integral S j dot ds is the total equation for the I enclosed. Okay. Then the current density means the current per unit area. As we know that current density means current per unit area, and it is the outer conductor and is along the minus kz direction. Hence, J can be written as previously in the first case we have considered the evaluation for J, that is pi by I by pi a square. Now here the radius along with the thickness we have considered for the path L3 range will be B to B plus T. Hence, in place of A, these are the two variables. If you substitute, then J becomes J equal to I by pi into upper limit as B plus T and lower limit might be B. Hence, I by pi into B plus T whole square minus B square into AZ. Why? Because here the radius is given by A power 2. Hence, the two limits are to be substituted as j is equal to I by pi into b plus t whole square minus b square along the z direction. Thus, I enclosed is equal to, as we know that I enclosed is nothing but previously we have considered I plus integral s j dot ds. Now, it is the direction there we have considered negative direction as minus az. Hence, I minus I by pi into b plus t whole square minus b square. Then integral along the z direction means the formula for ds is equal to rho d phi into az. Hence, the two differential elements are d rho and phi. By default, we know that the two ranging variables means phi is ranging from 0 to 2 pi and rho is ranging from, generally it is b to b plus t. Right? Why we have considered in place of b plus t rho means, again if we consider in place of upper limit rho by b plus t, so that limits will be substituted means b plus t whole square minus b square. Then this numerator b plus t whole square and the denominator b plus t whole square minus b square gets cancelled. Then I minus I becomes 0. But according to the path Ampere and path 3, that current total enclosed by that path L3 will not be equal to 0. For that, instead of substituting b plus t, we just consider here as rho. So, phi equal to 0 to 2 pi d phi, then rho equal to b to rho and rho d phi. Now, if we substitute here in place of this one, to simplify this equation, then I minus I by pi into b plus t whole square minus b square. Then for this, if we substitute phi component, then that is, if we substitute limits as 0 to 2 pi, it will be 2 pi. Then this is rho square by 2. Then limits are here b2 rho into d rho. So we evaluate this one rho square by 2 and the limits are b2 rho. Then that equation to be simplified as I minus I by pi into, so b plus t whole square. If we explain this one equation in terms of a plus b whole square formula, a square means b square plus d square plus 2bt minus b square, the denominator. Then that is 2 pi and here rho square by 2. Then if we substitute limits as b2 rho, that is the simplification equation, which is equal to I minus I by, so pi into b square plus t square plus 2bt minus b square. So this b square and this b square gets cancelled. T square plus 2bt into 2 pi into, means this 2 and this 2 gets cancelled. Then pi into, the substitute limits as rho to b, then rho square minus b square. So here, and this pi gets cancelled. Then I minus I into rho square minus b square in the numerator, and in the denominator t square plus 2bt. Right? So this is the equation which we have got. Means if you take here out of these two, I is common, then I into 1 minus rho square minus b square by t square plus 2bt. Then h phi equal to I by 2 pi rho. Means from this I enclosed is equal to, this is the equation, and by default we know that h phi means integral L h dot dl is equal to h phi into 2 pi rho. Then from that h phi equal to I by 2 pi rho into, the total equation is 1 minus rho square minus b square by t square plus 2bt. Right? So consider this as equation number 3. Why? Because till this we have evaluated 3 paths, 3 Amperian paths, h phi equations. Now coming to the fourth region, means that the region we have considered is rho greater than or equal to b plus t. And if this is the condition case, we use the path L4 as the Amperian path. So for this, if we evaluate that equation, means integral L h dot dl is equal to I enclosed, where this equation integral L h dot dl is similar for the 4 conditions, that is h phi into 2 pi rho. Now if we consider this I enclosed, means I enclosed is equal to, till path L2 the current is I, and from path L3 to L4 if we consider, it will be minus I. So this and this gets cancelled. Total net current which is enclosed by that path L4 will be 0. So I enclosed is equal to 0. Now instead of substituting, if you substitute in place of I enclosed by 0 in that equation, then this is the equation. H5 into 2 pi rho is equal to 0. Then from that H5 equal to 0. So consider this as another equation. Now from all the four parts we will approximate the equation. Means that will be given by here H is equal to. So there four regions we have considered. For the first region we have considered path L1 as the Ampere path. The region is considered as 0 to A, that is 0 less than or equal to rho less than or equal to A case. We have considered path L1 as the Ampere path. Then that is the case H equation is to be evaluated as I rho by 2 pi A square into A5. Then coming to the second region, if we consider as A less than or equal to rho less than or equal to B, then path L2 as the Ampere path. So this is the case. The total current which is enclosed by that path will be equal to I. Now if we consider like that, the equation which we have got in the second case is I by 2 pi rho into A5. Now coming to the third region, that is B less than or equal to rho less than or equal to B plus T case, we have considered path L3 as Ampere path. Now from this, if we evaluate, means the total net current which is enclosed by that path L3 will be I plus the total. Hence that I enclosed is given by I plus integral S J dot ds. Now from that H5 means or H component magnetic field intensity H is given by I by 2 pi rho into 1 minus rho square minus B square by T square plus 2BT into A5. And for the last case means the fourth region, that is rho is greater than or equal to B plus T case, we use the path L4 as the Ampere path. Now this is the case till path L2, the total current enclosed by that path L2 will be I, and for this path L4, the net current which is enclosed by that path L4 is given by minus I. Hence, total current enclosed by that path L4 will be given by here I minus I, hence that is equal to 0. If I enclosed is equal to 0, then there doesn't exist magnetostatic field, hence H component becomes 0 in that particular case, right? So this is the way we have evaluated four conditions for the infinitely long coaxial transmission line. There we have considered four regions as 0 to A to B, B to B plus T, and B is greater than or equal to B plus T case. We have evaluated in all the cases magnetic field intensity H. That is, H is equal to I rho by 2 pi A square into A5 for the first case, I by 2 pi rho into A5 is for the second case, and I by 2 pi rho into 1 minus rho square minus B square by T square plus 2BT into A5 for the third case, and which is equal to 0 for the fourth case as rho is greater than or equal to B plus T. Now for all these conditions, if you draw a plot between magnetic field intensity versus the radius as rho, then the plot will be given by like this. So the first region we have considered as 0 to A, means 0 less than or equal to rho less than or equal to A, and the second region, that is A to B, A is less than or equal to rho is less than or equal to B, and third region is B to B plus T, this is the region, and last case is rho is greater than or equal to B plus T. So for all these cases, if you draw the plot between magnetic field intensity to the rho component rho, this hence if you observe the first case, that means 0 to A case, the relation between magnetic field intensity H and the radius rho. So here if you observe, these two are directly proportional to each other. Hence, if you are going to increase the value of this rho, automatically the H component is also to be increases. Hence, the linear increment is observed here. From 0 to A, there will be a linear increment. That is to be given by I by 2 pi A from 0 to A. Now if you observe the second condition, that is A to B, means I by 2 pi rho into A5. Now if you observe the relation between H component and rho component, it will be inversely proportional. Hence it is decaying curve, right? Inversely proportional from A to B. This is the curve which we have got. Next, from B to B plus T means that component is given by H is equal to I by 2 pi rho into 1 minus rho square minus V square by T square plus 2BT. So, parabolically means curved. Again, if we compare A to B, B to B plus T, again it will be less. So, and if you consider the fourth condition, means rho is greater than or equal to B plus T case, it will be equal to 0. Why? Because here the total net current which is enclosed by the path L4 is 0. Hence, Hy component for the fourth condition is to be 0. Hence, B to B plus T, it will be almost equal to 0. Then B greater than T case, it won't exist. Hence, this is the way we can observe the changes from different regions from 0 to A to B to B to B plus T2, then greater than or equal to B plus T case. The change we have observed, that is between magnetic field intensity H2 and the rho component, right? So, how we have evaluated the magnetic field intensity in this case is, firstly, from this figure we have evaluated, means this figure is given by here infinitely long coaxial transmission line, means the cross sectional part of the coaxial transmission line we have considered. So if you observe, there exist two concentric circles which are having the inner radius as A and the outer circle radius as B and thickness as T. So depending upon these three parameters, we have 4 Amperian paths. So that is the path L1, here from here to here it will be path L2. From this is path L3 and outer line, dotted lines represents path L4. For all these 4 possible regions, we are going to estimate magnetic field intensity, right? So the regions 4 we have considered is 0 less than or equal to rho less than or equal to A and A less than or equal to rho less than or equal to B, then B to B plus T and rho is greater than or equal to B plus T. So in all the possible cases, we are going to estimate the first condition. If you consider path L1, the range will be 0 less than or equal to rho less than or equal to A. Then this is the course. We are going to apply the magnetic Ampere circuit law, that is I enclosed is equal to integral L H dot dl. In each and every region and each and every Amperian path, we have separately evaluated the equations for I enclosed and integral L H dot dl. For all the cases, we will be evaluating the equation for H component. And coming to the second also, for path L2, we use the region as 0 less A less than or equal to rho less than or equal to B. This is the case also. We have evaluated the equation for H. Now, if you consider path L3, the region we have considered as B is less than or equal to rho is less than or equal to B plus T. This is the case also. H we have evaluated. Next, last case, that is path L4 case, we consider the region as rho is greater than or equal to B plus T. So this is the case also. We have evaluated magnetic field intensity H. So from all these cases, we have evaluated magnetic field intensity, how it is varies from each and every respective cases. Now from all these, we have finalized the magnetic field intensity H as for region 1, 0 to A, it will be given by I rho by 2 pi A square into A5. And for A to B, it will be I by 2 pi rho into A5. And B to B plus T, we use path L3 as the Amperian path. Then that is the case I by 2 pi rho into 1 minus rho square minus B square by T square plus 2BT into A5. And for the fourth case, we use path L4 as the Amperian path. Region we have considered is rho greater than or equal to B plus T. Then H component is equal to 0. So this is the way we have finalized all the 4 cases as 1, 2, 3 and 4. So from all these 4 possible regions, we are going to draw one graph, a curve between H5 versus rho component, means magnetic field intensity H versus rho. So from 0 to A, we observe the relation between H and rho, there will be a directly proportional. Hence, there will be linear increment if you observe 0 to A. Then from A to B, then if you observe the relation between H and this rho, it will be inversely proportional, hence it is decreasing curve. And if you observe the third case, that is B to B plus T case, it will be the relation is inversely proportional, and again it will be given as B to B plus T, it is decaying curve. Now from fourth case, that is rho greater than or equal to B plus T case, HFI component won't exist, hence rho is greater than or equal to B plus, hence HFI is equal to 0. So this is the way we have evaluated all the applications of Ampere's law. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.